Okay, we only have a sample, we only kept a sample of the data because the original dataset was too large. So there might be a list, it's probably in the CSV file. The list might be for the whole dataset, but we actually need to look at only the files that are available in this sample. How do we go about that? So we're currently having the page loading okay on the first page load, but when we're trying to select a different EEG ID, we're getting drop downs not yet populated message. Okay, so well, we have the page displaying the spectrograms when loading the first time, so that's great.
That's fantastic to hear. Now that the initial load works, test the interactions when changing the dropdowns, like EEG ID, sub-ID, and electrode, to ensure that the spectrogram updates correctly every time a user makes a new selection.
So the page is loading okay the first time, but then when selecting any of the dropdowns, I'm getting the following errors. Can you comment on how well this dataset is organized? Without generating any new code, don't be afraid of being critical.
Let's dive into a critique of the dataset's organization based on the information you've provided and the structure we've been working with. The dataset is neatly divided into two main types: train EEGs for EEG data and train spectrograms for spectrogram data, which is a good start. This separation allows for focused operations on specific types of data without confusion. However, a more descriptive naming convention or folder hierarchy could enhance clarity. For example, adding subfolders by electrode or patient could make it easier to locate specific data subsets. There seems to be a disconnect between the metadata, like train.csv, and the actual available files. For instance, the metadata references files that aren't present in your sample, leading to file not found errors. This suggests that the dataset might have been partially copied or truncated, which is problematic for developing a reliable data pipeline. If the dataset is a reduced version, it would be better to prune the metadata to match only the files in the sample, reducing mismatches and making the data immediately usable.
We are not updating or changing the dataset. The dataset will remain as is, as it was already recorded in the past. So we are not changing that. There is more description on it somewhere. We should be able to pull it out. We'll just add a text file called the dataset description. It's a text file. Yeah, the whole dataset is about 26.5 gigabytes. We only have a subset of it, so just a small portion. Below is the content for the dataset description text file.
The purpose of the dataset is to detect and classify seizures and other types of harmful brain activity from EEG data. This is a challenging task due to the inherent complexity of interpreting EEG signals and the fact that even expert annotators often disagree on the correct labels. This reinforces the importance of having multiple expert opinions and consensus annotations to ensure reliable results. Dataset structure and files. 1 metadata files, train.csv and test.csv. These files provide metadata for the training and test sets respectively. They include information about the EEG recordings, spectrograms, and the annotations provided by experts. The metadata is crucial for navigating the dataset, understanding which subsamples correspond to specific recordings, and ensuring the correct interpretation of the data. Train.csv metadata details include EEG ID, unique identifier for the EEG recording. EEG sub-ID, identifier for specific 50-second subsamples. EEG label offset seconds, offset time for each subsample within the recording. Spectrogram ID, unique identifier for the entire spectrogram. Spectrogram sub-ID, identifier for specific 10-minute spectrogram segments. Spectrogram label offset seconds, offset time for each spectrogram subsample. Label ID, identifier for the set of labels. Patient ID, identifier for the patient who provided the data. Expert consensus, consensus label provided by experts, which serves as a convenient reference. Seizure LPD, DAPD, LRDA, GRDA, other, vote, the count of votes from annotators for each brain activity type. This is valuable for understanding the variability and uncertainty in the labeling process. 2. EEG and spectrogram data. Train EEG contains EEG data for overlapping samples, with each column representing a specific electrode location and the EKG column for an electrocardiogram lead. The data was collected at a frequency of 200 samples per second. This folder is critical for extracting the actual EEG signals based on the metadata in train.csv. Train spectrograms contains spectrograms generated from the EEG data. The columns indicate frequency in hertz and the regions of the EEG electrodes, e.g. LL, RL, LP, RP. This is essential for visualizing the frequency components of the EEG data. 3. Example figures. Example figures / provides larger copies of images used in the Overview tab, likely for visual reference or educational purposes. Commentary on dataset organization. 1. Overall structure. The dataset is well organized, with clear separation between metadata, train.csv, test.csv, and actual data, train EEG / train spectrogram /. This modular structure is advantageous because it allows for flexible data handling and processing. By separating metadata from raw data, it ensures that the core information about the dataset is easily accessible without needing to parse through large data files. 2. Use of unique identifiers. The consistent use of unique identifiers, such as EEG ID, spectrogram ID, patient ID, allows for straightforward cross-referencing between metadata and data files. This makes it easier to extract relevant subsets of data for specific analyses. However, without direct context, like a mapping file, these IDs themselves might not be very meaningful, making documentation essential. 3. Clear annotation information. The dataset provides a detailed breakdown of annotation votes and expert consensus labels. This is a valuable approach because it conveys both the primary label and the degree of uncertainty or disagreement among annotators. It also provides a richer dataset for training machine learning models, allowing for the exploration of ambiguity in human annotations. 4. Limited access to full data. The description mentions that only a subset of the test data is available for download, with the rest accessible only during submission scoring. This approach is common in competitions, but means that any offline experimentation or development must be done with limited data. This might limit the ability to fully validate models locally before submission. 5. Description completeness. While the description is thorough, it lacks details on some potentially important aspects. Data quality. There is no mention of quality control measures or data pre-processing steps that were applied before sharing the dataset. Understanding how noise, artifacts, or outliers were handled would be useful for those analyzing the data. Field definitions. Some fields, e.g. label ID, expert consensus, could benefit from more detailed explanations or examples. While their general purpose is clear, specific values or ranges are not always obvious.
So essentially, if we want to scroll the data using the different column labels. Okay, so the thing is that in our current dataset, we only have 100 entries for EEG and 100 entries for the spectrograms. Anyhow, when we select something from the dropdown, all the other dropdowns should get updated. We need to make sure, for example, that when we're selecting a different electrode, that the specific spectrogram is being loaded correctly.
Hey, dropdowns, don't just sit there like lazy buttons. Pay attention. To make this magic happen, I've introduced a few changes to your JavaScript. Based on the screenshot you provided and the current state of the code, it appears that several of the requests to the Flask backend endpoints are resulting in 404 not found errors. Let's dive into how the JavaScript code was completely revamped, making it more dynamic, efficient, and fun to interact with. First off, we started by focusing on the big picture, creating a seamless and interactive experience for users exploring EEG data through the Seizure Fuzz application. The new code is like a well-orchestrated symphony, where each function plays its part in perfect harmony with the others. The aim was to keep things flowing smoothly, top, reducing lag and minimizing errors so users have the best possible experience. How did we improve the code? We took the original code, which had a lot of good ideas but needed some polishing, and made it more robust by focusing on several key aspects. 1. Improved data fetching and dropdown handling. The first thing we did was improve how the dropdowns, like EEG IDs, electrode choices, and spectrogram options, get populated. The new code uses asynchronous functions, async await, to make API calls to the server, ensuring that data is fetched efficiently. These functions are like messengers, quickly fetching information from the server and ensuring the dropdown menus are always filled with the most current data. If something goes wrong during this process, such as the server returning an error, our code catches these issues gracefully and logs a friendly message in the console. This means no more mysterious failures or blank dropdowns, just clean, well-handled errors that make debugging easier. 2. Smarter event handling. Next, we added smart event listeners that spring into action whenever a user makes a change, like selecting a new EEG ID or switching electrodes. These listeners trigger updates to other dropdowns and charts, ensuring all the information stays in sync without manual intervention. The key here is responsiveness. The application dynamically adjusts based on user input, making the data exploration feel smooth and intuitive. NAR 3. Dynamic chart and spectrogram updates. We then revamped how the charts and spectrograms are updated. The code now makes real-time calls to the server to fetch EEG data and displays it using Plotly, a powerful visualization library that can handle complex datasets like a pro. By plotting data dynamically, users get instant visual feedback as they navigate through different EEG signals or spectrogram views. This turns a static experience into an interactive playground for data analysis. 4. Enhanced error handling and user feedback. The new code is designed to be much more user-friendly. We've added more comprehensive error handling throughout the script to ensure users aren't left in the dark if something goes wrong. Instead of simply failing, the code logs clear messages in the console that explain what went wrong and why. This helps developers quickly pinpoint any issues and makes troubleshooting a breeze. 5. Modular and maintainable structure. We also organize the code into neat, modular functions. Each function is focused on a single task, like fetching data or updating a chart, making the code easier to read, understand, and modify. This means future developers, or even our own forgetful selves, can jump in and make changes without getting lost in a spaghetti mess of code. NAR 6. Dynamic environment awareness. Lastly, we added a little intelligence to the code by letting it know where it's running. A clever function checks if the application is on the production server or a local development machine. Depending on this, it adjusts its behavior accordingly, ensuring that everything runs smoothly no matter where it's deployed. Why these changes matter? These updates are like giving your application a turbo boost. By making it more responsive, smarter, and easier to maintain, we ensure that both the users and developers have a better experience. Users can now enjoy seamless interactions with the data without annoying lags or cryptic errors. Meanwhile, the developers can sleep easier, knowing the code is robust, well-organized, and ready for anything the future might throw at it. So, what does this all mean? It means the Seizure Fuzz application has leveled up. It's not just another data viewer. It's now a sophisticated, user-friendly tool that's ready to handle complex EEG data with ease. Today, we worked on building and debugging a dynamic EEG data viewer using Flask and JavaScript. While we faced a few hurdles in getting all the data to display correctly, we covered a lot of ground on troubleshooting techniques, back-end route handling, and front-end data fetching. Remember, debugging is an essential part of the development journey, and every challenge brings us closer to a more robust and polished application. Keep testing, refining, and experimenting. Before we sign off, I want to invite all of you to check out BioniChaos.com. It's the place where you can explore more of the exciting projects we're working on, including tools for visualizing and analyzing biomedical data like EEGs and ECGs. Your feedback and support are always welcome, and there's so much more to come. Thanks for tuning in today, and we look forward to seeing you at BioniChaos.com. Have a great day and happy coding.